Hello. So today I'm going to do something I've been wanting to do for a while. I'm going to go through a textbook of linear algebra, normal textbook, normal linear algebra, and I guess for those who don't know what I'm doing around here, I'm going to try to do it in this graphical way. I wanted to give you an idea of what a textbook goes through. If I ever wanted to write a textbook myself or something, I kind of want to play with that. So this is literally the first PDF I found of a intro to linear algebra. I've noticed that in some videos, like there's some horrible mic noises when I touch the tablet in some way. I hope I don't do that too much, but we'll see. Okay, here we go. I've only read a few pages ahead, so I'll try to be surprised by what's happening. Copyright, I'm not supposed to have this PDF, I guess. Here's what I'm noticing first. They're talking about vectors. I'm not talking about vectors in graphical linear algebra. We kind of start immediately from equations as a thing, so we'll see how that goes. And I'm tired today, so we'll see how far I can actually go. All right, preface. What does it say? Linear algebra is pretty and okay. Is this interesting? I don't think it's interesting to me. Let's skip structure. We'll see. I want to get started. Okay, chapter 1, vectors. The heart of linear algebra is interior operations, both with vectors. We add vectors and we multiply them. It doesn't even explain what. Okay, am I going to gender that person right? I'm guessing it's a he. Gilbert something, right? Okay, I'm good. So he doesn't even explain what vectors are. It's just like, okay, his vectors, we can just add them. Which is pretty rough, but okay. Yeah, so as I said, graphically, vectors, not really a thing. Graphically, I just have variables like, x, and then I add, 3y to it, and oh god, I can't, this is very annoying. I didn't find a way to extend the margin, so I can't write here. So this is what things look like in graphical linear algebra. We don't really have vectors. We have a bunch of variables, but we never sort of treat them. We rarely treat them as the vector, as a particular thing we would have operations on. It's not really relevant. It's kind of relevant if we start thinking about, maybe those are maps or spaces of vectors, but even then, like, I don't know how much we need that as a concept. So I was just gonna skip all the vectors. I don't know. I'm gonna do how am I gonna do any linear algebra if I skip all the vectors? We'll see. Okay, so some linear combinations represent vectors v. I don't know who my target audience is for this. I'm assuming someone who's done, linear algebra and knows what this is about. Vectors in 3D. Woohoo! Getting exciting. Okay. The important questions. For one vector u. Okay, we're talking about spans and linear combinations. This is pretty neat. This links to geometry, and I guess that's a question I don't know how to treat in graphical linear algebra, despite the graphical name. I don't know how to talk about geometry, the geometry of things. Like, we definitely have, like, lines, I guess. Do we have lines? Like, even dimension of things is not a very natural question. There's the number of wires, like, number of variables, I guess, but that's not always the dimension of the thing. Yeah, I guess there's a question to be explored here, but, like, should I skip ahead? Should I get distracted by this? No, I'm just gonna keep in my head. Geometry is hard to do graphically. Let's remember that. Here's the key ideas. A vector v has linear combinations, and then some kind of geometry thing, and then examples. I don't care about that. Problem sets. Lengths and dot product. Okay, that's more vectors, angles, key ideas, problem set. Matrices. Yeah, but I still don't care. Even matrices, I don't really care. Okay, so the way to do matrices is that they take vectors and then they use matrices to they combine the vectors into a matrix. That's one way of saying it. And then the other way is that they sort of, oh, here's a way to write a linear combination, I guess as a shorthand, or here's a way to describe all the linear combinations of those three things, which is, yeah, that's definitely very interesting as a concept. But man, is it different from the way I do it. Like matrices sort of arise in my world. How do they arise? And they're like, it's a pattern of operation you observe. I guess I can explain how matrices arise in my world. I've done a video on it, but I feel that would be relevant. Somewhat, I don't know. I'm so tired. I'm going on automatic here. It's quite funny. Okay, let's remove this disgusting background. This notebook, basic. I hope that works. Oh, that's gonna take a long time. It's a long notebook. I think I'm overloading my app as well. It's not the best app. If anyone knows something better on Android, then I'm keen. It's called Incredible, this one. Okay, matrices. Why do we get matrices? They sort of arise did it arise naturally? Okay, I mean, what even is a matrix? Here's a matrix in the normal way of doing things. We just had an example here, matrix. And it's a thing, I guess one way of saying it is it's a thing that acts on vectors. Well, it takes a vector and gives me a new vector, and this new vector is calculated in this particular way. Okay, sure. So that's A, and that's some vector X, and that's like Y. And the way I write this graphically is that we can just write, AX plus BY. That's easy to write, right? Okay. This is multiplication by B, multiplication by A. So I take X, I multiply it, I add those two, and then I get, this is AX plus BY. And then I also want this one, so that's CX dy. And like, this is, you don't reuse variables, that's not a thing. You need to be explicit about the fact that it's the same by using the black dot, which does equality or copying, depending on how you see it. Okay, so this is, let's call this VW UV. This graphical equation is the equation, U is AX plus BY and V is CX plus DY. This is the same equation written in a different form. And this equation can also be written in, yet again, a different form, which is the one we want to get at. This is the matrix ABCD applied to this vector is this vector. Those are three ways of writing the same thing, right? AX equals Y if we give names to things. So far, if I do it like this, I don't know why I'm doing this. There's no justification for now. The way they justify it is, let's look at all the combinations of these three things. And I don't really know why this is important. Why is this important? This A is a difference matrix. What even is that? Okay. That's me. differences of numbers. Okay. And this whole textbook is just very much not the way I was taught things. This is I really want to say this feels American, and it's like sort of hands-on. Here's the thing, and like just sort of I don't know. There's a particular brusqueness to it. I'm used to a very different brusqueness. I'm used to a way of doing it where you're just like so precise and rigorous. We're just like, ooh, let's define all the things and be very precise about where we need that, and not even that. They're just like, here's a vector space. Like they haven't mentioned vector space. They've mentioned vectors. Like here's a vector space and linear maps and shit. This is a very different extreme. All right, dot products. That works. Linear equations. Yeah, here we go. We're finally going to where I want to be. And also, I don't know if it shows how tired I am. I'm like, I don't really know what I'm saying. But I'm doing this because it's fun. Up to now, the numbers x1, 2, and 3 were known. The right-hand side, b, was not known. Okay, I guess this is an interesting angle. We found that vector of differences by multiplying ax. Now we think of b of known, and we look for x. Ooh. Okay. New question, that's the inverse problem. How do we solve this? Most linear systems are not easy to solve. Indeed. Indeed. And that's that's another thing about... Oh no, I hate this background. Whatever. That's another thing about GLA in graphical linear algebra. That I might have some equation. Maybe this is x and this is b, and I want to find the x that gives me b. And how do you even do that? I guess a lot of linear algebra is learning to solve, right? And so if the actual equation is something like this, this is like ax equals b. That's the way I would write it. A matrix A would be in this sort of asymmetrical shape. I call that a spaceship shape. And that means ax equals b. And how do you solve this? Is like, I guess, a big question of the algebra. Probably that's kind of the whole point. Is it the whole point? Okay, what does he say? What does he say? How do we do it? Ah, here we can find it, because it's a lower triangular. What's a lower triangular matrix in graphical land? That's a good question. Let's write this matrix. This is a fun one. And what I found most helpful is reading this bit, right? Because we've got CDE, that's sort of the inputs, and I want to compute this as the outputs. So C goes to the first output, and then actually you have D minus C, so I guess let me copy C. I'm gonna need to copy D as well, and then I'm going to add D to minus C. So the square here is, take the minus. Okay, I should space things out more. And then, okay, so here on top we've got C. Here we've got D minus C, right? So D plus minus C. And then here we want E minus D, so same shit. That's E minus D. All right, this is the way you write this. This matrix, or rather, this equation is this pretty neat, like squiggly line. And now, question is, how do we invert this? I mean, is that the question? That might be the question. And note that the labels are only here for me when I want to convert between the sort of normal and graphical land. But the actual matrix is this thing, right? The labels are not like relevant. This is the thing that does operation. If I plug any number here, it will give me some output. All right, let's duplicate this one. Duplicate. And wait. Oh wait, no, inverting matrix is later. Here we go. So now we have this and we want to solve it. What does it look like? What does that look like graphically? We want to solve it, so we know some b's, and here, note that they want to solve it in the general case, right? For any b's, they want to find the x's. So they're literally inverting the matrix. So here I have some map A from right to left, and it's written as a map in the sense that it's easy right now, given if I give you 3 inputs, it's easy to compute the 3 outputs from the way it's written, because you can just follow from left to right. Then you get like you have a 3 here, then you get a 3 here, and -3. You have a 2, -2, a 3, so that's like 1, and that's -1, and here we go. We've computed sort of from left to right, easy peasy. But from right to left, it's not as easy to compute, because here's, I don't know if I could, here's my example. Sort of output, can I compute this way? Well, this works, but then this 2, like, I don't know what to choose. Like, is it 1, 1? Is it 0, 2? It's not clear. I would need to sort of go back and forth and get back and forth. So there's oh, actually, this is not too hard. There's a sort of, there's a sort of way I might be able to write this that makes it easier to compute. And, well, we can't figure it out. The way I would do it right now, it's sort of jumping at my eyes. I just want to do it from looking at this. Is that the things that are easy to compute from left to right are those ones. That's the thing that's easy from left to right. Things that are easy from right to left are literally just the symmetry, right? Those ones. Those ones, if I have inputs here, then I get outputs easy. The other way around, not so much. So I kind of want to twist any of those into any of those if I can. And I can, because, for example, I know that this thing, I can bend, if I sort of bend the leg of that thing, I get this. There's a minus, like it's sort of turning a plus into a minus, and there's a -1 that pops up. I guess I could justify why this is true. You just write it, and it looks, that's like A, B, C. This is B plus A equals C, right? And this is A equals C minus B, which is indeed the same equation. So those two graphical equations are identical. And if I use it here, I can, well, I guess how do I use it? I mean, I guess I'm using it the other way around, but then I can replace this bit by a bit like this, and then this sort of bendy thing. It's very important to keep track of which is input and which is output, because if I get too sloppy, and if I go like this, for example, you don't really know which is input, which is output. Like, is this like this one plus this one equals this one, or the other? Like, you might make this is what a sign error looks like in this language. This is actually kind of funny. A sign error is literally when you like get too sloppy with the way your legs are bent, and this literally get a sign error. All right, carrying on. I swapped one of those. This one I can also do this thing, and then turns out like this equation is just, this is just equality of all 3 things, right? So it's I can write it like this as well. It doesn't change. I can bend the leg of the black dot as much as I want. So this is the same as this. And this one also, how do we use? Yeah, this one. Output one here, and then this one I'm gonna move. Move. So what do we get? I have played a bit around with bending legs and shown the following, which is kind of cutely symmetrical as well. Those are like I just bent some legs from here and then got this. Where's my eraser not working as well? What's funny about this one is that this one is made of things in that direction. So it should be easy. Actually, I can't reach because of an interface issue. All right. This is what I've used. This I can erase. This one is easy to compute from right to left. If I give it 1, 2, 3, then this one just is copied here. That's 1. And then here I have 1 and 2 coming in to a plus, so that's just a 3. The 3 gets here, and then there's a 3 here, so that's a 6. So this is, those are the same equation. The exact same relation between the 6 variables on the wires. But this one is written in a way that is clearly computable from left to right, and this one is clearly computable the other way around. And you can, both of them are equal to a, and they're also equal to a minus 1, sort of going the other way around. That's sort of what the inverse means. And so here we've done what they do here, which is going from this to this, is rewriting the equations. It's literally like, here's 3 equations, here's 3 other equations, and they're equivalent. Oh man, I'm ranting so much. It's been 20 minutes. I don't think I'm going anywhere with any of that. I don't even know if I should publish this thing. But, well, here we go. We've inverted one matrix. I've justified none of what I'm doing. I should get a nap. Yeah, A is invertible. Yay. Fun times. And indeed, here to talk about invert matrix. I don't think I'm getting a lot from doing this right now. So I'll come back later. I had fun. I hope you had fun too, watching them.